Camille, Siftronic.
Assalamualaikum warahmatullahi wabarakatuh. Good morning everybody. Selamat pagi. Welcome. Kita pakai bahasa Indonesia dulu lah ya. Jadi welcome untuk webinar kita yang ke-23 ya di Laboratorium Terpadu USU. Kami dari Lab Renewable Energy ingin menyajikan teknologi terbaru dari lithium baterai yang memang banyak digunakan ke mobil listrik hari ini gitu ya. Jadi terima kasih atas waktunya. Thank you very much for coming. We really appreciate for the speaker Ridwan Ahmed. How are you?
Yeah, I'm good.
Okay, thank you. So thank you for your time. I know it's night in US right now in Seattle, but we really appreciate for your time to giving the talk for us. We really appreciate for all the interest from all the staff, the university around. I think from the registration, we receive a lot of interest from like many of university. Like if I can mention it, there's University Medan Area, there's a Polytechnic Wilmar Business Indonesia, thank you so much. University Negeri Medan, Universitas Sari Mutiara, Universitas Islam Indonesia, welcome. IAIN Kendari, Universitas Cudnyadin, Universitas Malikul Saleh, Politeknik Tanjung Balai, Universitas Kristen Indonesia, Politeknik Negeri Medan, IAIN Araniri, UIN Araniri, Universitas Muhammadiyah Sumatera Utara, Universitas Nahdlatul Ulama, PTKI, Universitas Di Hasan Bengkulu, welcome, UIN Raden Fatah Palembang. So we are very thank you for the interest for this webinar. We really appreciate for the trust. First of all, we would like to thank you, the head of the laboratory, Ibu Rahmi, and the head of the sub laboratory in Lab Terpadu USU, and all the staff and the student in Universitas Sumatera Utara. So thank you very much. Today we will have a webinar about electrifying the future. So what's next in lithium battery technology? Ridwan Ahmed, it's one of my I could say a best friend. So we spending time in Boston or in Worcester for several years together. So he did mechanical engineering or material, they say mechanical materials engineering in Worcester Polytechnic Institute. And right now, he's working as the battery researcher in Pacific Northwest National Laboratory. So one of the national lab in Indonesia in Washington. So again, welcome Ridwan. So after this, we're gonna have the Indonesian anthem. So for Oki Hadinata, slide is yours. Thank you so much for Oki Handinata. So we would like to welcome Febri Rizky SSE for the praying session. So Febri Rizky, slide is yours.
Assalamualaikum warahmatullahi wabarakatuh. Sebelum memulai kegiatan webinar Electrifying the Future What Next in Lithium Battery Teknologi hari ini, marilah kita tundukkan kepala dan hati kita sejenak untuk bermunajat sekaligus memohon ampun kepada Allah Subhanahu wa taala. Semoga webinar ini dapat berjalan dengan baik. A'udzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Hamdan yuafi nikmahu ya rabbana walakal hamdu walakal syukru. Allahumma sholli ala Muhammadin fil awalina wal akhirin. Allahumma ya Allah ya Tuhan kami, dengan mengucapkan puji dan syukur kehadiranmu atas segala rahmat dan karuniamu yang telah Engkau berikan kepada kami. Allahumma ya Allah ya Rabbana ya Karim. Jadikanlah kegiatan webinar ini sebagai awal kemajuan laboratorium kami untuk memberikan bekal ilmu sebagai penyelenggara perguruan tinggi yang bermanfaat bagi civitas, mahasiswa, dosen, alumni kami sebagai pemimpin masa depan kelak. Ya Rabbana, acara kegiatan webinar hari ini ditujukan tidak lain hanya untuk memperoleh ridhamu semata. Untuk itu berikanlah petunjuk dan bimbingan kepada kami agar kami dapat menjalankannya dengan baik. Allahumma ya Allah ya Rabbana ya Karim. Jadikanlah kami semua yang mengikuti kegiatan webinar hari ini untuk menjadi generasi unggul di masa depan yang dapat bermanfaat untuk diri sendiri, keluarga, masyarakat, bangsa, dan negara. Iyyaka na'budu wa iyyaka nasta'in. Rabbana taqabbal minna innaka antas samiul alim wa tub 'alaina innaka antat tawwabur rahim. Semoga Engkau mengabulkan doa kami. Amin ya rabbal alamin. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you so much for Febri Rizky for the praying. So after this, we're gonna have opening speech from Dr. Insinyur Rahmi Carolina, STMT IPMGP. So Bu Rahmi, the time is yours.
Thank you very much. This is Echa. Assalamualaikum warahmatullahi wabarakatuh. Good morning. May peace be upon us all. Distinguished guest, Professor Pope Angelisa Sibuan, as a Vice Rector 3. Our distinguished speaker, Dr. Ridwan Ahmed, Ph.D. Good evening, Dr. Ridwan, from the Pacific Northwest National Laboratory, United States of America. All the head and staff in the Integrated Laboratory, USU, respected faculty members, lecturers, researchers, students, and all participants. It is truly an honor and pleasure for me to welcome you all to the 23rd edition of our webinar series, organized by the Integrated Laboratory of Universitas Sumatera Utara. Today's theme, Electrifying the Future, What's Next in Lithium Battery Technology, is both timely and vital. As we stand at the forefront of a global energy transition, the development of advanced lithium battery technologies is essential to support clean energy system, electric vehicles, and sustainable innovation worldwide. So we greatly honored to have with us Dr. Ridwan Ahmed, Ph.D., a highly accomplished researcher at the Pacific Northwest National Laboratory in the United States, with a strong academic background in physics and material science. Dr. Ridwan specialized in computational modeling, including first principles calculation and finite element modeling, lithium battery components such as anodes, cathodes, and solid-state electrolytes, as well as structural and mechanical characterization techniques like SEM, XRD, and mechanical testing. His remarkable dedication to research and innovation has earned him numerous accolades, including the Outstanding Performance Award at PNNL, the Best Graduating Student Award, and Second Best Innovator Award at the African University of Science and Technology in Abuja. and also the academic excellent award from Ahmadu Bello University in Zaria, Kaduna in Nigeria, if I'm not mistaken, because I see your LinkedIn actually, Dr. Ridwan. So we are confident that his insight and expertise will inspire meaningful discussion and foster a deeper understanding of what lies ahead in lithium battery technology. On behalf of the organizing committee, I would like to express our sincere gratitude to all participants for joining us today, and to everyone who contributed to making this event possible, especially Mrs. Reza Ikwani, Ph.D. We hope this webinar provides valuable knowledge and open opportunities for future collaboration and innovation. So thank you very much and enjoy the session. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much. Welcome back to you, Miss Echa.
So thank you so much for our head, Dr. Rahmi. So the other session we're gonna have a picture frame, ada foto bersama. Jadi silahkan mungkin kalau boleh dihidupkan kameranya, it will be appreciated. Thank you so much. If we can put the camera on, Ridwan, so we just wanna have like some of the documentation online.
Baik,
So
bagi,
for data, session.
baik bagi peserta webinar, baik bagi peserta webinar yang bisa menghidupkan on camera, please. Ya, kita tunggu sebentar, beberapa masih ada yang belum. Baik, siap. 1, 2, 3. Baik, sekali lagi. 1, 2, 3. Baik, sudah. Saya kembalikan ke Bu Reza. Silakan.
Thank you so much for Dinata. So a little bit introduction. Oh, sorry. Okay, a little bit introduction for our speaker. Our speaker is Ridwan Ahmed, as mentioned from Bu Rahmi earlier. He's already spending a lot of time in battery technology. Since I met him, he's doing like material preparation, also like battery assembly, perakitan baterai, also dimensional functional theory to see like the property of the material or the battery itself, even the mechanical properties. So he did the Doctor Philosophy in Worcester Polytechnic Institute. He did 2 master, first in Material Science and Engineering in African University Science and Technology, UST. And also he did a Master of Science in Material Science and Engineering in King Fahd University of Petroleum Minerals, KFU, PM. And after that, upon the graduation, he joining as the associate researcher in Pacific Northwest National Laboratory, one of the national lab in US. So his knowledge is very beneficial for us, and it's hoped to be additional exposure for our lab, especially for renewable energy in lab Terpadu. So a little bit before we move on to Ridwan Ahmed, a little bit about Renewable Laboratory USU. We okay, sorry. Bukan. Okay. Hah? Sorry. Slide yang terbuka apa? Oh, sorry. 1 second. Okay, a little bit about renewable energy. We just want to mention that we have ability for the training equipment relating to renewable energy. So we have a solar generation system, refrigeration system, wind power, solar beam, hydrogen system, and some of like small portable equipment like thermal imaging, thermal anemometer, wireless weather, sound level, thickness devices, and some of them, which is we have the ability in this lab. So we really would like to invite people like, I know some people coming from different universities. So if you have like um, classes related to renewable energy and you need a place to have the hands-on training how the renewable energy system works, so you please welcome to come in Lab Terpadu USU. So this is the ability that we have. So I just want to share to make people aware that we have this ability in USU. So please welcome, especially for classes renewable energy in USU environment and also university outside. So please welcome. I think that's all. I'm coming back to Ridwan. So how are you, Ridwan?
Yeah, I'm doing well. Can you hear me?
Yes, so we can hear you well.
Okay.
So we're really excited for your presentation. So it will be around 40 to 1 hour session. We're gonna have a question and answer in the at the end. So I think that's all. I think from now you can share your presentation. So slide is yours. So thank you so much, Ridwan.
Thank you. Can you see my screen?
Yes, we can see clearly. Thank you.
Okay. Just a second.
Sure. Take your time.
Okay. There you go. Okay. Yeah. Hi everyone. Assalamu alaikum wa rahmatullah. First and foremost, I would like to extend my sincere gratitude to the organizer of this webinar, to the esteemed faculty of Sumatra Utara University. I hope I pronounced that well. And also to all the participants. It is a great honor, for me to be invited here today to give a talk on lithium battery technology. So again, my name is Ridwan Ahmed, and I work at the Battery and Material System Group at PNNL, Pacific Northwest National Lab. And the picture you're seeing on my screen is actually our beautiful Richland campus, which is about 1 hour flight from Seattle, which is in Washington State. A lot of people, if I just tell them Washington, they used to think it's Washington, D.C. So they're actually different. In fact, they're far from each other. So Washington, D.C. is actually different from Washington State. So today, the topic of our talk today is electrifying the future. What is next in lithium battery technology? First and foremost, I would like, I know a lot has been said in terms of giving like an introduction about me, but I would still like to give a quick overview about my background.
So Ridwan, sorry, are you going to put the slide? Because we couldn't see your slide actually.
Oh, you cannot see my, oh,
Yeah,
I
we
thought you
could.
could see.
So we just see.
Oh, okay.
Okay. Sorry.
Okay.
for this.
1 second. Yeah.
All right. So we can see your slide now.
Okay. Perfect. Sorry about that. Yeah. So, let's see.
Sorry, Dr. Ridwan, to interrupt you. Yeah,
Yeah.
I think from the previous slide. Okay.
Yeah. Can you see?
Yes, we can see your first slide right now. Like Pacific place.
Ah, okay. So I can go ahead, right?
Yes, please. Thank you.
Oh, okay. Okay. So just a brief overview about my background. I'm originally from Nigeria. Nigeria is the most populous country in Africa. Our capital city is Abuja. And according to 2023 estimate, I think we have about 236 million people. I think, the latest estimate is even more than that. So there are so many tribes, but the major ones are the Yoruba, Hausas, and the Igbo. I was born in Kaduna City, that's the northwest Nigeria, and the major tribe in Kaduna is Hausa. But my dad and my parents are from Kwara State, which is like north central, and they are from Yoruba tribe. But because I was born and bred in the north, that's in Kaduna, I can speak both Hausa and Yoruba language. And talking about my academic background, I would like to be fast with it because I believe a lot has been said already. So I would like to start from my high school. I attended Ansarudin College High School. And I'm going to show, some, pictures of like people who actually assisted me and, contributed significantly to my academic success. One of them was late Mr. Moshood Bello, who volunteered to be my private tutor when I was in high school, when he saw, my potential. And at the time, my parents couldn't afford to even send me to like, private, tutorial classes. So this man actually volunteered to kind of to teach me complex concepts in mathematics and physics. But unfortunately, he's late. May his soul rest in peace. So after my high school, I went to Ahmed University, one of the best universities in Nigeria. And of course, that was where I studied physics. And I would like to mention this one that you're seeing his picture here, Professor Tajuddin Ahmed. In fact, he was the one that actually made me to remain in physics because at some point in time, I wanted to change my course of study because at the time, we felt like, it's only engineers that do great things. So we wanted to, become engineers. So I wanted to switch to engineering, but I was like, you're doing great in physics, and physics is also a great course. So, and I never regretted, that. So after my bachelor's degree, I went to African University of Science and Technology under like fully funded scholarship by World Bank. And after that, I just, went to King Fahd University of Petroleum to do another master's in material science and engineering. So during this time when I was in the Kingdom of Saudi Arabia, I also got the opportunity to do 3 months internship at King Abdullah University of Science and Technology. This is actually a beautiful university with outstanding facilities, and they also have like world-class faculty. And again, about these universities, I would like to encourage students among us who might, want to I just wanted to mention that there's a lot of opportunities in terms of like fully funded scholarships from master's and PhD programs in these universities. So following these, I went to WPI, Worcester Polytechnic Institute in the United States, and that was where I did my PhD, Material Science and Engineering. And I want to specifically, talk about this man who was my advisor, and I think he was also the advisor of Russia. So he was very, very, supportive, and he happens to be a kind of person that just wants, his students to be successful. And after my PhD, as I said in the introduction, I got an offer to work at Pacific Northwest National Lab doing research on lithium batteries. Now back to the business of the day. Fundamentals of lithium-ion batteries. So basically, the schematics I'm showing here just shows, the major components of lithium-ion batteries, which are the cathode, separator, anode, usually soaked within, in the electrolyte. And what happens is that, when you're charging your battery, basically what you're doing is that you have these cathodes. For instance, this is one of the most commonly used cathode material, lithium cobalt oxide. This actually gets decomposed where you have, release of lithium ions and electrons. So at this time, the lithium ions migrate or moves from the cathode through the separator towards the anode. And the electrons move through the external circuits. So this is what happens at the anode. Usually the anodes are made of carbon materials like graphite, and you have these, electrochemical equations, right, happening at the anode. So, and when you discharge the batteries, the reverse occurs. What do I mean by that? So the lithium ions that move from the cathodes to the anode now change their directions by moving from the anode to the cathode. So that's basically what we do when we're saying we're charging and discharging our battery. We are basically moving lithium ions from one side of the battery to the other side of the battery. And these are common anodes, that are used in the lithium-ion batteries. And these are like graphite and silicon. And common cathodes include all these transition metal cathodes like lithium cobalt oxide, lithium manganese oxide, lithium iron phosphate, and the rest of them. And common electrolyte is basically like dissolving like some common salt like lithium, LiPF6 in some organic solvents, EC, DMC, or ECEMC. And of course, this, examples of separators that we often use in lithium-ion batteries are polyolefin separators like polypropylene and polyethylene. But people, especially those that are not, in this area of research, they don't basically know the difference between lithium-ion battery and lithium metal battery. There's actually a difference between the two. And that's quite simple. So when you have lithium-ion batteries, it's basically the anode is like, made of, like I mentioned in the previous slide, it's made of like graphite, or you have silicon, right? But when you replace this anode, you replace it with like lithium metal, then that becomes lithium metal battery. That's just the basic difference. So you're replacing the graphite anode with lithium metal, that makes it lithium metal batteries. Why are we talking about lithium metal batteries? We're talking about lithium metal batteries here because if you look at this graph, you see these are like, common batteries that are in the market. You have the lead acid battery. If you look at the energy density in terms of like the volumetric energy density and gravimetric energy density, you can see that as you move from lead acid to, let's jump to lithium ion, you can significantly increase the energy density of your battery. But if you simply replace the graphite anode with lithium metal anode, you can even increase the density further. But we have a challenge here, which is the safety. And I'm going to talk more about that in the subsequent slides. When did you even start, doing research on lithium metal battery? I think one of the notable research that was done, on lithium metal battery was the one done by Stan Whittingham in the 1970s, where he simply used lithium anode and then titanium sulfide cathodes. But what hindered the development of this battery was this issue of, safety, because this battery is highly flammable, like it can easily catch fire. But just around the same time, Goodenough and Yoshino, came up with, replacing the lithium with graphite and then using a different cathode material, which is lithium cobalt oxide. They were able to develop lithium-ion battery. And since then, this battery, became commercialized, and it actually revolutionized the consumer electronics, the laptops, the phones, headsets, mention it. You will find lithium-ion batteries there. And in recent times, we are even thinking about, we're using these batteries in electric vehicles, for grid storage and of, renewable energy. But because of these new applications, we now have like a more stringent requirements for batteries. Because, we want a battery with very high energy density so that, for instance, the electric vehicles can cover a longer range and compete with the gasoline vehicle. And we also want batteries that have high rate capability, meaning that you want to, for instance, charge your battery as fast as possible, especially if you're using it in electric vehicles, of which the current lithium-ion batteries have certain, limitations. There's a level you can go in terms of the energy density. And of course, we also want batteries that are not, that are cheap, because the cheaper the battery gets, the cheaper we get, all these, like, let's say, electric vehicles and, some other stuff. And that is why researchers, continue to, do research on lithium metal batteries, because when you replace the graphite, like I showed in the previous slide, when you replace the graphite with lithium metal, so you can achieve like higher energy density. So we started working on lithium metal battery again. But the problem still remains, the problem of safety, and also the capacity can drop, very fast. And on this slide, I just wanted to show, like, a market focus for lithium metal batteries from 2018 to 2034. You can see that there is, kind of steady growth in terms of the CAGR of lithium metal battery market, and that's going to grow up to about 124.84 in 2034. And, applications-wise, you see that for electric vehicles, there's going to be a significant jump in terms of the market size, as it was in 2023 compared to what it will be in 2032. And even in energy storage, there's going to be a significant jump. And also, I would like to mention some big players in terms of, like, lithium metal battery research and development. And these are some key companies like Solid Power, QuantumScape in the US, you have Samsung in Korea, and you have CATL in China. So all these things, I'm showing these just to show, that there's, a significant effort towards, moving, not really moving. It's not that we're trying to replace lithium-ion batteries with lithium metal batteries, but we're just trying to bring this into the market in such a way that, it's going to augment or support, the current lithium-ion batteries. So let's go back to the challenges of lithium metal batteries. So when you have your lithium metal anode, the bare or bulk lithium usually has like a thin layer on top of it, which is like a decomposition product. We call it SEI. What is an SEI? Basically, SEI stands for solid electrolyte interface. And that's the decomposition products arising from the reaction between lithium and electrolyte. Sometimes may not even be electrolyte. Just lithium is very reactive. You just put it, even expose it into air, it's gonna get reacted, and you can have, components like lithium oxide and all sort of things forming on top of it. And typically, this thin layer that we call SEI is usually lithium ion conductive. It can allow lithium ion to pass through it, while it's block electrons to, pass through it. So what happens is that when you charge your battery, when you plate the lithium, you add some additional lithium on top of it. One of the challenges we have is that we want to have uniform lithium deposition, but that's not what you get all the time. So this is the kind of things you get, like tree-like, and that is called dendrite. So this dendrite is actually not good. You don't want to have it. As you strip it, you tend to have this residual SEI, and in the long run, you tend to form some kind of dead lithium, which is like, it doesn't have any contact with the, the bare lithiums. So it's kind of inactive. It doesn't participate in the chemical reactions any longer. So what happens is that when you discharge your battery for a long time, so this is what you get. You tend to form a lot of dead lithiums. So your active lithium becomes, completely consumed, and even your electrolyte, which is, continuously reacting with the lithiums, also gets dried up. And the result is this: when you're using a practical battery where you use very thin lithium, which is like a 50 micrometer thick lithium, the capacity drops faster. In other words, the cell fails, within a short time. And the same thing goes with if you use a very lean electrolyte, because for practical battery, you want the lithium to be as thin as possible, and you also want the electrolyte not to be much. You want lean electrolyte. So if you're using those two for practical batteries, the battery can easily fail. That's basically what we're trying to show with these graphs. Remember, I talked about this dendrite, this tree-like. So the challenge, one of the problems it can cause is that it can grow in such a way that it's going to penetrate through the separator and have a contact with the other side of the battery, which is the cathodes. And that is not good. It can cause fire, because that is what we call short circuit. So those are the challenges surrounding lithium metal batteries. Dendrite formations. You also have, also there's also a large volume change as you deposit or you plate the lithiums. It's, the volume changes is significant, and that can, cause, mechanical failure of the SEI. Because usually you want the SEI to be there so that it can prevent further reactions of the lithium with the electrolyte. But if the expansion of the lithium is significant, it's going to break it up, and you'll have continuous reactions, and that will cause the battery to fail. So how do we solve these problems? There are various strategies by which you can solve all these problems. And the first one is electrolyte engineering. So, people have thought about, okay, how about if we make like solid state electrolyte? The reason why, because another problem that I forgot to mention in the previous slide is that, this battery, if you use liquid electrolytes, mostly these liquid electrolytes are flammable, because the solvents you use are highly flammable. So they can easily catch fire. So if you use solid state electrolyte, you can reduce the flammability, you can improve the safety. And also because of the, you now have solid materials, right, in your batteries that can prevent or mitigate the growth of dendrite. So I highlight this in green here because I'm going to talk a little bit about this. And other strategies under electrolyte engineering is you can develop some advanced liquid electrolyte, which is part of what we do in our lab, that can form this, for instance, it can form a very strong SEI that we're talking about, that's not going to break easily and it's going to be ultra thin, so that once that is formed, you're not going to, have that continuous reaction of lithium with, electrolyte. So it's also part of what we do in our lab, but I'm not going to talk too much about that today. So we also develop gel electrolyte, which is like in between the solid and the liquid electrolyte. It just combines the advantages of liquid electrolyte in terms of improved ionic transport properties and then the advantage of solid state electrolyte. So the other approach is interface engineering. And one way to go about this is you can deliberately form your solid electrolyte interface, and that is called artificial solid electrolyte interface. So you just form that layer on the lithium, and with the belief that that layer will prevent further reactions of lithium with the electrolyte. And like I noted here, a stable and robust SEI or ASEI helps reduce side reactions between electrolyte and the anode, which is the lithium. And that improves, if you're able to achieve that, that would improve the stability of your battery. So let's talk about all solid-state lithium metal batteries. What that means is that everything is solid. Because in this case, we are not talking about liquid electrolyte, just using solid-state electrolyte. And the main advantages is that when you use solids, like I mentioned before, it's going to be what? Less flammable. And also, it can mitigate dendrite growth. And that can help achieve improved stability and safety of the battery. But what are the main challenges with this kind of batteries? One is high interfacial impedance and capacity loss. Because now you have solid-solid contact. So if there is no proper contact between this, let's say solid electrode and the solid electrolyte, then the impedance will be high. In other words, the resistance to the lithium ion flow will be very high, which is not good for the battery. So this contact strongly depends on the pressure we use to bring, the components together when we are making the battery. And that is why one of the work I did, and I think with Risha too was also part of the work during my PhD, was we tried to model like solid-state batteries as shown in these schematics, where you have the electrodes, you have the electrolyte, and you have lithium. So we tried to use finite element modeling to, study the effect of pressure on the contacts and the induced strain, in the electrolytes and also in the electrodes. So by so doing, we'll be able to, identify the optimal pressure that we can use to make our battery that's going to, ensure that we have that improved contact and we are not inducing failure into our system. And as we can see from here, if you start from 0 megapascal of pressure, you see that for contacts, you see that space there. But when you increase the pressure to 0.26 megapascal, that improves the contact. And the strain is not so high. But when you go to 1 megapascal, even though you have improved interfacial contact, but you can see that the strain is so high. And they have gotten to a level where, they can induce like cracking, mechanical failure within the electrode, which is not good for the battery. So we tested the electrochemical, we did some electrochemical measurement just to look at, the ionic conductivity. And we found out that, we got the optimal or the maximum ionic conductivity when the pressure was 0.26, which is in line with what we got from the modeling that, shows that at 0.26, you can have, optimal contact without inducing failure in your material. So that is one of our contributions to, making sure that we have better solid state batteries. Now, talking about the other part, remember I mentioned you can also do interfacial engineering where you make like artificial solid electrolyte interface. So making artificial solid electrolyte interface is quite easy. It's just coating your lithium metal with some materials, but they need to have certain properties or characteristics. And again, like I mentioned, this method is very easy, it's scalable, and it's cost effective. So this is showing that if you just have your lithium without any coatings, without any, artificial SEI, you can easily form that dendrite. But with coating or with that artificial SEI, you can, achieve stable cycling of your batteries without, forming all these dendrite. As a quick note, if you want to form a good SCI or a good surface layer, it needs to have good chemical stability so that, because it's going to have, it's going to be in contact with the liquid electrolyte. So if the chemical stability is not as good, then it can react with the electrolyte. And that can damage the artificial SDI. Again, it needs to have good ionic transport properties because you still want your lithium ions to be able to, go in and out, during charging and discharging. And of course, you want it to be robust because you're still going to have this, when you plate the lithium on the lithium metal anode, you're still going to have this increase in, volume, of which if the SCI is not strong enough, it's going to break it. And that's it, it's gone. So you're not going to have that protective effect again. So this is one of the, strategies that scientists, researchers, use to improve the stability of lithium metal batteries. So this is one of my work at PNNL. So in this area of research, so basically what we did is that we have this lithium metal, and we had this coating, which is like composite polymer, a combination of PEO. PEO is a commonly used polymer electrolyte with LLZO. And then, so we have these composite coatings on the lithium. And after that, because this PEO also has some issues, the chemical stability against some of the electrolyte we use is not as good. So we wanted to, improve on that. So basically, we now had an additional layer on top of it, which was some kind of surface treatment. That's why we call it surface treated composite polymer electrolyte. And this is the procedure shown here. So after forming the composite polymer layer, we coated it into the solution of the, the solution we use for the surface treatment. After that, we treat it with UV light, and we have this layer on top of the lithium. So these are the SEM images of the coated lithium. So this is the, coated lithium, and this is the cross-sectional image. This is the copper, which is the current collector. The dark region here is the lithium. And what we have here, STCPL here, is the coating. So whenever we have this, we do some quick tests, preliminary tests to be able to show that, okay, when you have this in your batteries, you can achieve better stability or improve performance. So this is one of the tests we usually carry out in the lab, where, we have lithium symmetric cells. So you have lithium here, you have lithium here. So, and what you just be doing is that you just be moving lithium ions, you plate, strip, and you do it for, as long as possible until, the cell fails. So you can know how long the cells can, the number of cycles it can withstand before it fails. So if you look at the black line here is just the bare lithium. Nothing is done to the lithium. And you just put it in the symmetric cells. So if you look at it, you can see that after some times, the voltage, which is what we call overpotential, it's kind of, increases significantly relative to the, this red one or orange. So now we have this black, which, the overpotential is now, it increases. And after some times, what happens? It fails. When you have this kind of fights, we feel like the battery has failed. But if you look at the second one here, which corresponds to the protected lithium, that is the lithium with our protection layer, with our layer on top of it, it can withstand a longer cycle. You see, up to 750 hours compared to the bare lithiums. So what this tells us is that the protection layer we have on our lithium actually shields the lithium against side reactions with the electrolyte. So following this, we now make a full cell. So in a coin cell. So we have a coin cell, you have your cathode and you have your anode. And these are the kind of tests we conduct to be able to check the efficiency, the stability of our batteries in the lab. So the black line here is the bare lithium. Bare lithium means nothing is done to the lithium. We just take the lithium, we use it as anode, and then combine it with the cathodes. If you look at this graph here, you can see that the capacity drops very fast. But when you use the lithium with the coating layer, which is our coating layer, that can withstand a longer cycle number before it starts dropping. So if you want to think about this, like, okay, if we use, that means if we use the bare lithiums in, let's say, lithium in electric vehicles, what that means is that, it's just a guess here, like maybe if after 1 year, the bare lithium fails, then the protected lithium, which is the lithium with the coating layer, can still, work for like additional 1 or 2 years before it fails. And this one is just showing the efficiency here, which is about 100% for the protected lithiums. And if you look at this black line here, that is for the bare lithium. That is also close to 100%, but it's fluctuating, and it's still lower than that of the protected lithium. The last graph here is the kind of test we conduct, to check the rate capability of the battery. We wanted to know what happens to the capacity or to the energy density when you charge it very fast. Because typically when you charge battery very fast, it tends to, lower the capacity of the battery. So we wanted to see, okay, if we charge it at higher rates, what's going to happen? Or if we discharge it at higher rates, what's going to happen? So relative to like if nothing is done to the lithium. And as we can see from here, as you continue to increase the charge rate, what happens? Although the capacity decreases for both, but it decreases more with the bare lithium than the protected lithiums. So all these things is just telling you that when you have this, a good protection layer on the lithium metal anodes, you can significantly improve the performance of the battery. And it's quite simple. Like I mentioned, it's just coating the material on top of the lithium. And then, but you just need to make sure you find the right materials with the right combination of properties. So after cycling our cells in the lab, we also do what we call post-mortem analysis. Like we try to check all those electrodes to see what's happening to them. So one of the things we do to, especially the anode part, which is the lithium, is we just take the SEM images like after cycling to see what happens. So if you look at the SEM images we have here, the left figure here is just the bare lithium, and all this black, white, all these things you're seeing here just shows that the lithium has severely degraded. And that corresponds to the performance we got in the previous slide. That, okay, after certain cycles, it drops very fast. And that's why we're having that sharp drop in the capacity of the battery. But if you look at the protected lithium, we can still see that protection layer on top of the lithiums. So the lithium is beneath and you have the protection layer. So that shows that it's still kind of protecting it from reacting with the lithium ion, or with the electrolyte. So that's one of our contribution in terms of, like, trying to improve on the stability of lithium metal batteries. So this is another contributions we made, where we try to use a different material in this case and a different method. So in this case, we use molecular layer depositions to just deposit what we call liticone. Liticone is just a combination of lithium salt with some kind of polymer material, that's glycerol. And so we use that to form a layer on top of lithium metals, to form like an artificial SEI. So this is just, I'm not going to talk too much about this. This is just the molecular deposition process, molecular layer deposition process. And these are the SEM images of the deposited, of the coated lithium. So this is the deposition layer, which is the liticone. This is the code name, LIGL4. 4 means 400 cycles. That's the number of MLD cycles. And we did like FIB plot to just look at the cross section, and then we found out that the coating thickness was actually 1 micron thick. And we also did EDS just to confirm that this is actually our coating, because carbon is like the characteristics element. So like we did in the previous work, or before then. So sometimes what we do is that we just coat, we can coat the materials, what we have as the coating, we coat it on bare copper. We will not deposit lithium on top of it. We want to see whether that coating has good ionic conductivity or not. So we're going to see whether the lithium is deposited on top of the coating layer or beneath the coating layer. So that's what we did here. So this is bare copper. When you deposit lithium, this is how lithium looks like. In fact, this kind of morphology you are getting here is because the electrolyte we have is one of the electrolyte developed in our lab, which is one of the best in the world. That's why you are having this this kind of microstructure. For some conventional electrolyte, you're gonna see a lot of dendrite forming here. But this dent structure you have is because we're using good electrolyte. This is the cross section, which shows the copper and the deposited lithium. And now this is the coated copper. That is copper with our artificial SEI on top of it. So we deposited lithium, and if you look at the cross section, you can see that this is the copper, this is the deposited lithium, and this is the coating layer. So which means the lithium is deposited beneath the coating layer. That is what we want. Because if that happens, then that means the protection layer is going to protect the lithium from reacting with the lithium, with the electrolyte. Again, this is just EDS maps, just to show that, okay, we truly have, this is where our copper is. This is our lithium. Lithium is not showing here. It's hard to, detect that under EDS because it's a very light element. So that's why you see it's, it's dark region here. And the carbon, which is coming from the protection layer, is at the top. So that confirms that we have that coating layer on top of the lithium. Again, so this is one of the, like we did in the previous work. So we did this, we made this lithium symmetric cells, and we also conducted this test where we kind of studied the overall potentials of the cells over time. And you might see this LG1. We wanted to just try different thicknesses of protein layers. So that's what we have as lithium LGL1, 2, and 4. And we discovered that when you have 400 cycles, which is lithium GL4, that will give you the most stable cycling compared to the rest of the other options. And similar to what we did in the previous walk, we also, make the full cells. So we have this is a full cells. We have the lithium anode, and we have NT622 cathode. So that's one of the famous cathode materials that are used in, for various applications like EVs and all sorts of things. So when we made this cells, we tried to compare performance for the lithium coatings at different thicknesses. We compare with the bare lithium. If you look at the bare lithium, which is the black line here. Again, the first graph here, I think I didn't explain it in the previous slide. So this is just what we call the voltage profile. It's just for us to see how the voltage changes with, or how the capacity increases with voltage. So this is charge. When you charge, this is the capacity as you charge the cell. And this one coming down here is the discharge profile for the cells. Again, this can give you a lot of information about batteries, but that's not the main focus of this discussion. So now looking at this second graph here, we can see that the green line here shows it doesn't drop as fast as, like, let's say the black line. The black line is the bare lithium, nothing is done on it. So it dropped faster. And this one still kind of pretty stable up to about 200 cycles. I know some might question that, 200 cycles is still a short cycle. It's not for this kind of battery, because the conditions we have here is stringent. Like, it's a kind of, for instance, we're using 50 micron thick lithium. It's very thin, and then the current density we are using to charge and discharge the battery is high. In fact, if you are using conventional lithium, the conventional electrolyte, and you're using this kind of conditions, maybe the battery might not withstand maybe 40 cycles. So this is truly remarkable, having 200 cycles with this kind of conditions. And the efficiency, if you look at the efficiency, Coulombic efficiency for the battery with lithium DL4, it's pretty stable. Up to, in fact, the 200 cycle is almost 100%. Meanwhile, if you look at other options, especially the black line, you can see where nothing is done to the lithium, we can see that the efficiency is dropping so fast. And we also tested the rate capability, because that's the kind of test we also carry out to see, how this battery behaves if we charge it very fast. Why are we doing this? Because we are thinking about applying it for EVs. We want to charge the batteries as fast as possible so that it can compete with the gasoline vehicles. So, and if you look at this, it looks like the thinner coating on lithiums actually performs better here. And that's related to the fact that when you have thin coating, even the fact that the thickness is reduced, so the impedance might be, slightly lower than the thicker coating. So that's why we achieve like higher capacity here than the thicker sample, which is the green line here. But overall, what this is telling us is that you have that lithium coating on your lithiums, you can still achieve higher capacity even at fast charging rate. So similar to what we did in the previous walk, after 200 cycles, we dismantled the cells. So we carried out post-mortem analysis. So for the sake of time, there's a lot of things we did, but just to save time, that was why I'm just showing the SCM images. So these are the SEM images of the bare lithium and coated lithium after 200 cycles. Again, if you look at the bare lithium, we can definitely say that, you know, we say corrosion of the lithium is severely corroded or degraded. But if you look at the coated lithium, we can still see, even though, you know, there's still some degradation, but it's not as severe as that of the bare lithiums. So all this shows that, you know, one of the ways we can actually improve the performance of lithium metal batteries is to, you know, develop this coating layer, right, on the lithium. Of course, there are other strategies, and again, going back to the you know, the title of the talk, where, you know, I think the point is that what is next in lithium, you know, battery technology. I would say one of the things is that, you know, like a previous slide, is that, you know, people are thinking about reviving, and all they've been working on the research, and it's still ongoing, where people want to improve the, you know, the performance of lithium metal batteries, right? Of course, there are other things, a lot of things that is going on, but this is also one of the major things that is happening within the within this research area. So yeah, in conclusion, lithium metal battery is promising, especially if you want to, you know, achieve higher energy density. And I told you, as I mentioned, you know, in the previous slide, if especially if you're thinking about electric transportations, we want batteries with high energy density. And lithium ion batteries, it may be difficult for us to get such high energy density. But lithium metal battery has a number of issues, right? Including dendrite formation, you know, low efficiency, and interfacial issues, right? Interfacial stability issues, of which if these are well addressed, I think that's gonna help a lot in terms of like wide spread adoption of this battery. Advancing artificial SCI, which is one of the main things I talk about today, and also electrolyte process design still promise, because even in our lab, we've developed different kind of outstanding electrolyte materials, which, like I mentioned previously, which can form stable interface, and that can extend the cycle life of the batteries. And of course, major companies and startups are investing heavily in lithium metal battery development. And I think I mentioned some of these companies in one of my previous slides. So we believe that the lithium metal battery market will still grow significantly in the next, you know, couple of years. So with continued research and breakthroughs, lithium metal batteries could become more commercially viable and widely adopted in the next decade. Yeah, I would like to acknowledge the support I got from my colleagues at PNNL, Dr. Wushu, Dr. Jason Zhang, Dr. Kim Jung-young, and Dr. Kian Zhao. Also, we're collaborating with Professor Xiangbu Meng from University of Arkansas. They were the one that did molecular layer deposition for us, and also Dr. Kevin Caballo. I would also like to acknowledge, you know, Dr. Risha Ichwani, Dr. Adri Uder, for their support, you know, even during my PhD until now. And lastly, I'm going to acknowledge the financial support from the U.S. Department of Energy through the Battery Materials and Research Program. Thank you, and feel free to ask any questions or, you know, give comments Thank you so much.
Thank you so much for Ridwan. It was a very great result and presentation. I know in Indonesia it's hard to sometimes working on lithium because we don't have enough equipment enough to keep the lithium stable in the environment. So I think we will open for like 3 questions. Is there any question from the audience? You can put in chat either in Indonesia, bahasa Indonesia boleh atau English, or we can or you can just ask right away to Ridwan. Is there any question?
Be a question.
Sure. Adri Huda.
So, first of all, thank you so much, Ridwan, for a very nice question, a very nice presentation. Sorry. So I just have I don't know. I think it's not really related to the presentation, but I think it's also part of consideration when we want to develop the battery. So talking about the lithium metal and lithium ion metal battery, so do you really think there is quite a difference if we talk about environment? Let's say in this era, we know that it's a lot of battery also is already ongoing using on the electric vehicle or on device. And if we talk about development, we also think to sustainable material, circularity of the material. Do you think there is a strongly different if we talk about lithium ion and lithium metal battery in terms of environmental issues like recycling process maybe in the future, or the material using? I think that's from my perspective. I think I hope that you can get my question. Thank you.
Oh, sure.
Yeah,
We
okay,
just
go ahead.
wait to Ridwan. So is there any difference between lithium ion and metal in terms of environment?
Yeah, thank you so much, Adri. That was a beautiful question. And first and foremost, there's a lot of, I think that's part of, what is next in lithium battery technology. There's a lot of effort in terms of developing this recycling capability. So especially on lithium ion batteries. But the first thing I want to say regarding lithium metals and lithium ions is, remember I mentioned that one of the main advantages is the higher energy density. And what that means is that you even have reduced materials. For instance, if you're using like a lot of materials to achieve certain energy density, you're gonna have, if you have lithium metal battery, that's gonna, that will be reduced significantly. So that is even more, environmentally friendly. And also in terms of recyclability too, it's also recyclable. And I think there's a lot of effort on that as well.
Okay. How Adri Huda?
If you don't mind, just one more question. It's
Yeah.
a little bit of technical issue that when you show us about the surface treatment, when you put the lithium atop of like copper or yeah, copper sheets. So is it why do you need copper on the surface, like under the lithium metal? Is it like any specific reason why you put copper, or can we use another, maybe alumina or something? Just like a technical.
Yeah. So usually one of the most widely used current collector, because we need to have a current collector, right, beneath the anode. So one of the commonly used material is a copper for lithium anode, and for cathode is aluminum, right? And that's due to the, because you want to make sure you have a material that has high, good electronic conductivity, right? And also relatively cheaper compared to, but that doesn't mean that's the only material you can use. You can use other materials too. But because of the good combination of properties in terms of the electronic conductivities, in terms of the cost advantage, that is why mostly, and some other factors, that's why mostly we use copper as the current collector. but some other stuff too can be used. Just like, the cathodes, you also have different varieties of things, materials that you can use. So current collectors too, but the most widely used one is copper.
Thank you, Dr. Ridwan.
Yeah, thank you.
Adik. So there's a second question from the chat session. So Assalamualaikum, Mr. Ridwan Ahmed. My name is Muhammad Abduh Akram Agus dari undergrad physics student from USU. I'm currently working on my final project about sodium-ion battery and have a strong interest in battery research. And you mentioned lithium metal battery, which are promising but still face challenges in safety and scalability. Meanwhile, lithium-ion battery dominate the market despite resource and the cost issue. An alternative like sodium-ion and potassium-ion are being developed. Given your academic experience in Saudi Arabia, like KFU, PM, KAUS, and now in US, and considering China's aggressive advancement in EV and battery technology, what do you think? Which country, like China, Saudi Arabia, or US, do you think offer the best environment for R&D about battery, like sodium ion or lithium metal? And which would you personally recommend for graduate studies in this field? Thank you very much. That's a good question. It's my question too. So go ahead, Ridwan.
Yeah, that's a very good question. Which country would you recommend? Okay. I don't want to be biased here. Otherwise, I'll say, okay, just come to the US. But I think those countries, especially, to be honest, especially US and China, I would say they are doing, investing a lot of money into this kind of research. So I would say those two countries. And also, I think there's also a significant effort in terms of like developing, especially like, I remember my experience at Cal. There's a popular professor there, Usama Sharif. So he's doing a lot of work on lithium batteries. And in fact, recently, I think I got this information that I forgot the amount of money that was, kind of used to support these R&D in kind of lithium batteries. So it's a lot of money. So I think all these countries are really spending a lot in this because they know that's the future, right? So yeah, I think I would say more than that. So, I know there's something recently, but I think things will change, especially in the US. But I believe like if we're able to continue to show that yes, this thing is promising, I think even the recent kind of directions will be changed, and US will continue to take a lead in terms of like investing in this kind of renewable energy. Yeah. But overall, I think those three countries, whichever one that kind of works for you, I think it's a good option, to do your R&D or your research in this area of in this field of research.
All right. So thank you, Ridwan.
Yeah.
Thank you, Muhammad Abdul Akram Agus. So is there any question from the audience? Ada pertanyaan lagi? Oh, from the chat. So there's Assalamualaikum, Mr. Ridwan. My name is Gilang from Mechanical Engineering. So what do you think? How difficult the development lithium battery from coin cell to the bigger size battery? Like, do you think that the
How
development...
difficult?
Mm-hmm.
In terms of what? How difficult? I didn't get the last part.
Oh, like how the development, is it difficult to like transform from coin cell, like what you did for your research, but for for the bigger size of the lithium ion battery? What's the challenge?
once you have the right facilities, it's not difficult. The only challenge is that at every stage, you have challenges that are peculiar to that specific stage, right? So sometimes you might be doing something at coin cell level, but when you get to, let's say, developing like pouch cells or this kind, you might still face a different kind of challenges. So other than that, if you have the right facilities, it shouldn't be that difficult.
Okay. So thank you, Gilan. Thank you, Ridwan. And there's another question from class EBT, I think renewable energy, from electrical engineering. So my name is Rakesh Naidu, undergrad from electrical engineering. Would you share how the process of charging and discharging of lithium battery in your research, please? Thank you. Sorry, you're muted.
I didn't get the last part. How the process of charging and discharging lithium-ion batteries, how it works?
Yeah, how the process of charging and discharging of the lithium battery in your research.
So how it works?
Yeah, I think so. Like how to process to charge to discharge, like how to test it.
Okay. So basically, it's still kind of similar to lithium-ion batteries, like I explained in some of my slides. I don't know if you're still seeing the slide. But the only thing that's different here is that, for instance, when you're using, like I said, the major difference between lithium-ion and lithium metal is just the replacement of the graphite with lithium metal, right? So, but in this case, when you have lithium metal, unlike when you have graphite, where those lithium ions are just filling those, pores or whatever in the graphite, in this case, you're actually plating. If you remember that, I think the person is from physics or which.
Oh, from electric.
So you have this, you have this concept of metal plating, those kind of things, right? So basically what you're doing in that case is you are plating lithium, right? When you are when you are charging. So the lithium ions, move from the cathodes and then, gets plated on the lithium, right? The lithium metal anodes. And the reverse occur when you are discharging, where you just strip, we call it stripping. You're stripping that lithium from the lithium metal anode. So it gets converted to lithium ion, and that gets, transported through the electrolytes to the other side of the battery, which is to the cathode. So it's kind of similar process. It's just that now we have metallic lithium. So in this case, we have lithium plating and stripping. I'm not sure. I don't know if that's what the speaker is
Okay.
saying.
Rakesh Naidu.
Yeah.
Maybe you can just put it in the comment section if you have more questions.
Yeah.
I think maybe we can have 2 more questions, Ridwan. Is it okay?
Yeah.
Boleh satu?
Oh, sure. Dari Bapak Ladies Heru, UIN RFP. Silahkan.
Oke, saya pakai bahasa Indonesia ya. Mohon Mas Adri sama Bu Reza yang translate-nya. Terima kasih. Mungkin sedikit saja sih. Jadi ini sesungguhnya saya tidak paham ya lithium. Yang saya pahami adalah lipovo ya, lithium iron phosphate yang sedikit pernah kaitannya dengan PLTS yang seringkali dipakai gitu ya untuk pakai lipovo dengan siklus yang cukup lumayan 5.000 siklus ya umumnya 2.000 sampai 5.000 siklus gitu ya. Nah, ini sangat penting dan sangat diperlukan ya, di mana baterainya kapasitas tinggi begitu dan kemudian tahan lama ya. Kalau 5.000 atau 6.000 itu saya kira sampai 15 tahunan ya. Apakah siklus ini real adanya seperti itu, seperti halnya diinformasikan yang katakan 5.000 ya. Kalau dengan lipovo dimaksud siklus, dan kemudian keekonomiannya seperti apa gitu ya. Ya sekarang ini kalau baterai kan dibutuhkan pengecasannya cepat dan kemudian ekonomi ya, keekonomian. Nah, satu lagi atau yang kedua adalah PLTBG misalnya yang waste to energy, katakanlah di kelapa sawit, itu seringkali dihargai murah ya KWH-nya. Karena seperti misalnya di Sumatera Selatan itu sudah cukup surplus ya energinya gitu ya di berbagai area. Oleh sebab itu sehingga karena monopoli PLN listriknya tidak kompetitif lah begitu untuk PLTBG misalnya ya. Apakah memungkinkan? Jadi tantangannya ke depan saya lihat dalam konteks PLTBG memurnikan metannya atau menyimpan listriknya barangkali begitu. Nah, itu kan dibutuhkan berarti yang apakah mungkin LiPoFo atau lithium baterai ini bisa kapasitas yang besar begitu dan bisa menyimpan besar ribuan kWh katakanlah seperti itu, atau jutaan kWh begitu. Potensinya seperti apa? Terima kasih, 2 poin mohon pencerahan. Terima kasih Pak Ridwan Ahmed.
Oke. Satu Pak, PLT gitu maksudnya tenaga gas ya?
Betul, pembangkit listrik pembangkit listrik tenaga biogas ya.
Oh, biogas. Oke. Saya coba translate ya Pak.
Ya, siap.
Ridwan, sorry, we are using Indonesian, so we try to translate. I think maybe some of the people, if you can, kalau ada yang lebih ngerti mungkin bisa bantu saya kalau saya salah. So Ridwan, Bapak Ladies Heru is aware about LiFoPo. LiFoPo stand for lithium Fe phosphate, so LiFePO4. So, and they using for kind of like solar cell generation system, and they're using the LiFoPo battery for that. And they're saying that that LiFoPo, it stands for 5,000 cycles, so it's like around 15 years. And they have the higher density. And he said that, is it that real? I mean, is it real that there is a battery that stand for that 15 years for like 500 cycles? What do you think? I will go for the second one after this. What do you think, Ridwan?
Okay, I think yeah. So the question is it real? That's, I would say that is real, but the question is, if it's going to withstand that number of cycles, what are the conditions in terms of, like, what did they use to make the batteries? There are different kind of parameters, we consider when we're thinking about the cycle life of a battery, right? Like I mentioned in my presentations, you want to think about the thickness of for instance, if you're looking at lithium metal battery, what is the thickness of the lithium metal, right? For instance, I have a very thick lithium metal. That means I have a reservoir of lithium, right? So that means if it's very thick, I can continue to say, even if it's degrading, it can take forever before you actually see the true effect, right? The true, degradation of the battery. So it depends on the conditions. You see a lot of papers, people just report different things. Oh, okay, we can cycle this for as long as possible. But what is the current density they are using to charge the battery and discharge the battery? That's the question you need to ask. So usually people use like low current density, and they claim that, oh, this can withstand, like this can, be charged and discharged for several years. So it depends on the conditions at which you charge and discharge your batteries. But that's possible, but it depends on the conditions.
So I think Pak Heru, saya lanjutkan dulu yang kedua ya Pak. Okay. So the second question is, I mean, what do you think that the economic, perspective of this lithium metal? Because I mean, for battery, if we think about commercialization, we need a battery that can be charged fast. And I mean, economically competitive with, what we have right now. For example, like we have like fossil fuel, energy system in this country. What do you think? Like how economic this technology? What do you think?
I don't know how true this is, but I think I heard that, Elon Musk once said that people should invest in lithium, right? That's the new, I forgot how that is put, right? I think probably that's the new oil or something like that, if I said it correctly. So personally, that's my personal kind of based on my experience, and I would say that's the future. And I will also say the same thing, right? It's like the new oil.
Okay.
So yeah, that's the future.
Okay. So let me translate a little bit. So Pak Ladies, Heru, the first pertanyaan pertama, Livopo itu katanya tergantung pada kondisinya Pak.
Kondisi ya, oke.
Jadi mau sebesar apa komponennya, kalau misalnya tebal ya terdegradasi juga lama gitu kan. Terus kayak mana kita ngecasnya gitu, KWH-nya apa namanya, current density kita cas ke baterai itu besar nggak? Kadang-kadang pakai casnya
kondisi.
rendah ya memang dia akan lama gitu, tapi kalau tinggi mungkin akan berbeda gitu Pak. Kalau yang kedua, dia menganut, bukan menganut ya, tapi dia setuju dengan apa yang Elon Musk katakan, ya kan, pembuat mobil Tesla, bahwa katanya invest lah ke lithium karena itu ya future nanti katanya gitu kan. Jadi lithium itu seperti new oil, jadi minyak baru lah. Oke, terima kasih Pak Lady Seru. I think mungkin kita limit ya satu lagi, mengingat Ridwan juga di malam hari di Amerika.
Oh iya.
Jadi,
Terima kasih ya.
terima kasih Pak Lady Seru.
Terima kasih.
Selamat sore Bu, saya bisa tanya Bu?
Boleh? Dengan siapa Pak? Saya nggak tahu. Rizal Sinaga, silakan Pak.
Yes, yeah, it's a great presentation, Ridwan, and I would like to ask some question actually. The first one is, in your opinion, which one is the best one to coat the lithium using surface treated composite material, polymer or LIGL, lithium GL? Which one is the best one? And then I see there are some lithium GL 1, 2, and 4. So that number stands for what? And the last one, in comparison to nickel-based battery, what's the advantage of using that lithium-based battery? I think that's all. Thank you.
Okay. So thank you. Dari institusi mana Pak?
Institut Teknologi Dell.
Oh, teknologi kita. Oke.
Yeah.
Terima kasih Bapak Rizal Sinaga dari institusi Dell. Ridwan, do you get the question or do you want me to? It's okay. All right. So go ahead. There's a 3 question from Pak Rizal Sinaga.
Yeah, I think I got all the questions except the last one. So what's the advantage of lithium metal batteries over nickel-based? Is that what the question is?
Yes, that's correct.
Okay. So the first one, so the composite kind of coatings, right, on lithium metals, which one is better, right, between the Liticone, right? Can you still see my slide?
No, we couldn't see.
Okay. Please share. Can you see it now?
Yes.
Yes.
Oh, okay. So even from this slide, we can see that I know probably since I didn't mention that, so the composite actually shows better performance. So I would say the composite coating is better compared to the Liticone coating. The reason is that when you if you look at this performance metrics, you see that first NMC 811 was used here. Everybody knows that, like we all know that when you use NMC 811, it degrades faster than NMC 622. So when you use NMC 811, you even expect to see that faster capacity decay. But this can still withstand, up to like 300 cycles. In fact, this is not the cycle life, because we usually define cycle life of a battery as when the capacity drops to about 80% of its capacity. So even at 300 cycles, it's not 80%, it's 85%. So with this NMC 811. But for the Liticone, which is LIGL, if you look at the performance, you can see it's just 200 cycles. So, and it's even NMC 622, which even is more stable compared to, because when you're looking at the full cell performance, you're looking at both cathode and anode degradation. So in a nutshell, to answer that question, the composite one performs better. And I think it's one of the, for this kind of conditions, is one of the best so far. Because even in this paper, we try to compare with some of the best results that people have got for these conditions. Again, when you're looking at performance of batteries, it depends on the conditions that we get. Somebody will say, oh, I can get 1,000, 5,000, but look at the condition, it's very low. Okay. So then what is LIDL? It's lithium glycerol. So it's just glycerol with some kind of lithium salt. I think, yeah, if you look at, you might search this paper, you're going to get more information about it. We publish it in small structure. Yeah. Lithium compared to nickel base, advantage, higher energy density. That's the advantage. Yeah.
Thank you, Ridwan.
You're welcome. Yeah.
Decision, thank you so much, because we're just considering that it's gonna be late night for Ridwan in US. So thank you so much for your time, Ridwan. I think we really appreciate. Do you mind to close? Okay. So we really appreciate for your time. It's very insightful. I think Indonesia also, start to have a lot of interest on lithium-ion battery. Not lithium-ion only, lithium metal too. Like some of the research group trying to develop. And we hope we can have like collaboration in the future. Even like people here maybe can contact you for the collaboration in the future. So thank you so much for your time. We really appreciate from Universitas Sumatera Utara, from Integrated Laboratory USU. So I think that's all. I think I might too close to this webinar. Thank you so much for
Thank you so much, Ridwan. Yeah. So have a
Thank
good
you for
sleep.
having me. Yeah, thank you so much for having me.
Okay.
Yeah.
You
Good
should
night,
come to
Seattle.
Indonesia. You should
Yeah.
come to Indonesia one time.
Yeah, sure. I really look forward to it. Yeah. Yeah.
Thank you very much. Thank you so much, everybody.
Yeah. Bye-bye. Yeah.
Bye-bye.
Bye.
Thank you, brother.